Okay, so today we will have a short talk or a long paper review, as you prefer to see it. I will be talking about this paper entitled Predicting Many Properties of a Quantum System from Very Few Measurements by Huang, Queng, and Preskill. I'm not reading the whole names, no. And it's basically related with the topic of shadow tomography. Okay, so we'll let you know now what this is about. So a major problem in quantum information is the retrieval of information. So you can perform any kind of computation or evolution of your system, but characterizing the quantum state of the system is a big problem. Okay, because usually you need to perform like an exponential number of measurements in order to characterize the state of your system. So you need an exponential number of measurements to obtain a fully classical image of your quantum state. However, for most applications, you don't need to know the whole state, but you can know only part of the state, and with that part of the state, you can predict the properties of the state that you care about. Okay? So the problem of constructing this classical representation of the small part of information that you have about the state is what is known as shadow tomography, because you take like a shadow of the original state that only encodes or only preserves the information that you are interested in. Basically, that's the general idea. So the term was coined by Scott Aronson in his paper Shadow Tomography of Quantum States, and he formulated the problem of shadow tomography as I show you here. So given an unknown quantum mixed state rho of dimension d, as well as known two outcome measurements, E1 to EM, that is, each of these observables has either value 0 or 1, as you may think. Each of which accepts rho with probability, this is the probability to measure the outcome 1 in rho, and rejects rho with probability, okay, the complement of that, output the numbers B1 to Bm, which are within the range 0 to 1, such that they are very near to those probabilities, okay, so so that they are very near to those probability according to a value epsilon for all of the values that you want to estimate, which with a given success probability measured with this delta. Okay, so the problem is to do this via measurement of many copies of the state rho with the number of copies as small as possible. Okay, so the challenge is to approximate the expected value of many observables, E1 to EM, with as few copies of the state as possible, this K. Okay? So in the original formulation by Scott Aronson, this is the statement of the problem that he gave, and as you can see, we don't here. With this definition, we don't really care about the computational complexity of retrieving that information or the complex experimental difficulty to implement this kind of measurements or whatever you want to do. You only want to bound somehow the amount of states that you need to achieve those values. Okay. So in this paper, he also proposed a method to obtain a non-trivial method to reduce the number of copies that you need of the state to solve this problem. And in his method, basically, roughly, I'm not going to go deeply into that, but basically, he assumes they assume that they can do global measurements on subsets of the copies. So he has these several k copies of rho. Okay, he takes a subset of those copies and he performs global measurements on those copies. Also, taking the outcome of those measurements, he adapts the next measurement that he does. So it's a bit adaptative measurement with global measurements. It's quite a complex algorithm also in the computational sense, because it's quite demanding, because you need to have a classical representation of the state that you adapt with your measurements. So it is costly in the classical post-processing and also quite costly in the measurements that you need to implement because you need to measure several rows at the same time. So in the paper that I'm sharing with you today, they approach both of these problems, that the cost of the post-processing and the measurement process. So they focus on obtaining a method to measure the state and retrieve information from it, but so that the things that you need to measure are like hardware efficient to implement. So they focus on a quantum computer. So when we say hardware efficient, we mean single qubit gates, 2 qubit gates that are more or less assumed to be easily implemented. So this is like the overview of their method. The method has 3 phases. The first phase is the data acquisition phase. In the second phase, you build the classical image or the classical representation of the state, given the data that you have collected. And in the last phase, you make the predictions of the states that you want. Okay? So this, I prefer to write it down. Let's see. Can you see it? If not, I will go through the next slide, and that's okay. Yes, okay. So it's the data part. Okay. So in the data acquisition part, you have you have access to, you will perform, first of all, what you need is a set of unitaries, U, which is, let me see, the word is a measurement primitive, which means that these unitaries are tomographically complete, in the sense that if you took, if you measured all of the observables of these unitaries in your state to full precision, you would fully know your state. So this is a set of unitaries with a given probability distribution, uniform probability distribution, okay? So in their algorithm, in the data part, what they do is they repeat n times this step. So you have your state, you rotate your state with a u that you would take from this distribution, and now you measure in the computational basis, or another canonical basis, and you obtain a bit string as an output b. Now what you do is you store this in the if iteration, you save the values of the unitary that you have measured and the bit string that you have measured. This is pretty simple. So the whole process, the process of performing this rotation of the state and measuring the output can be seen as a quantum channel. So this quantum channel is an evolution of the state. That is, you can compute it mathematically by computing the expected value of this state according to the unitary and the output. Okay, so this basically is the transformation of the state that you have obtained after performing the unitary. So I think the dagger is in the other view. So once you have done this and you have this string, the string of the different values, as U is tomographically complete, can be shown that the mathematical map characterizing the quantum channel is invertible. So we can construct an estimator for the quantum state in the following manner. Okay, so the if values that you have obtained, if you invert this operator with the expression of the quantum channel that you have, you obtain a classical snapshot of your quantum state. And the nice thing is that if you average over all of the snapshots that you have taken, you obtain as the expected value of that, you obtain your original state. Okay, so the expected value of these observables is the original state. So the strings of different snapshots are known, or is what they call the classical shadow of your original state. Okay, so you have a set of different snapshots, 222 and 222. Yeah, constructed in this manner. Yes, please. Yes, for only a snapshot you measure once, and you need one copy of raw. So here you have used n different copies of your original state, because once you have measured it, you have fully collapsed it because you are measuring in a complete basis, and you only measure once. Yes, you perform this rotation, so you measure in a particular basis, random rotation, then measure. Yeah. So you don't have to really compute these values, but this is the concept. Only with this couple you can work also, but it's important to see that there is a correspondence between those two. Okay? Yeah.
If you only measure one, you have the string.
Mm-hmm.
Like it's probabilistic, maybe the snapshot that like it has not has information, but it has not information. It can be 1 or 0 depending on the snapshot. Has one information or other. Like if you only measure in the proper basis,
Mm-hmm.
measure in the perpendicular one.
Mm-hmm.
This string can have no information.
Yeah. Yeah, so the important thing here is that as the set of unitaries forms a tomographically complete set, I think it's impossible that you obtain no information for all of the possible measurements that you could have. Yeah. So if you perform many measurements, for sure there will be some outputs that will give you information, and other ones that will not. You don't know. You don't know which measurement gave you more information, because to know that you would have to know the state. I think that's the intuition behind that. Yeah.
You don't know you have n copies.
Uh-huh.
You don't know what is fake and what is real. How do you get the certain information for?
Yeah. So what you now can do is, once that you have this classical snapshot, you can perform predictions. So now I can estimate the expected value of an observable in the original raw, an observable O, can be estimated by the average of all of these things. For example, from V1 to N. I don't need this experiment anymore. So the idea is that you can estimate the expected value of an observable on your original state by computing the expected value of the observable in the classical shadows, in this case. And the thing is that so they don't perform exactly this average. It's like a means of medians of means average. So they perform the average in many different states and then compute the mean of that, or the median of that. And the nice thing of this part is that mathematically you can prove that the variance of that it's quite narrow. So it's more or less efficient, more or less. Now I will show you the performance guarantees that they have. Okay, but this is the basic idea. It's quite simple in a sense.
How do you construct the vector B? Because the B is the number.
Yeah, the B is the bit string. So you assume that as you are in a quantum computer, the bit string that you measure is directly related with the vector, the state in the computational basis. Yeah.
So the 0, 1, you transform it into a
yeah, to 0, 1. Yeah, that's it. Yes, but in the end, these computations are made with a classical computer. So, okay, so this is more or less what I have said now. Here I have the this is the algorithm that they use to compute the means. So it's not a direct average or a direct mean, because in order to reduce the influence of the outliers, you have to perform a little bit more sophisticated method, but it's quite intuitive also, because instead of taking all of the n's and computing the average, they compute the average in different subgroups and then get the median of that. And that seems to be more robust to representation. But yes, this is basically what I have written here, so it's the same. So regarding the performance guarantees, so this is the informal statement that they do in the paper, and then I will show you the more formal statement that they have in the supplementary material. But basically, so classical shadows, that is this string of size n suffices to predict m arbitrary linear target functions, that is m arbitrary expected values of observables, up to additive error epsilon, given that n is bigger than something in the order of the logarithm of m, and the maximum of all of these norms, that I will tell you now what these norms are, divided by the error squared, okay? So basically, it scales logarithmically with the number of observables that you have, and somehow depends in the norm of these observables, okay? Then the definition of this norm depends only on the ensemble of unitary transformations used to create the classical shadow. So it only depends in this U. It doesn't depend on the state, and that's important, because if it depends on the state, then without information about the state, you cannot really know how well it is working. But as we know that this bound doesn't depend on the state, then the problem of obtaining very little information is not that bad, because this is an upper bound. You may be doing better, but you will never know. So you have to work with your upper bound. So this norm that depends on the ensemble that you are using, they study two particular examples in the manuscript. One is the random Clifford measurements, so single qubit gates and CNOTs, basically. And if you use this ensemble of unitaries to transform your state and then measure, then your norm is more or less related with the Hilbert-Smith norm. Okay, so this Hilbert-Smith norm can scale with the size of the system, or maybe not. Can you see? Because yeah, or maybe not. But for some observables it does, for other it doesn't. But this is more or less the relation. And they also study random Pauli measurements with single qubit gates. This, for example, is a widely used method in variational quantum eigensolvers to estimate the value of the energy or things like that. And this can be bound, depends on the locality of the observable. So if the observable acts non-trivially on k qubits, then the bound is exponential on that number of qubits. Okay? So this method, intuitively, this method is better for operators that are local, and this method is better for operators that have a small Hilbert-Smith norm.
What does it mean to have a Hilbert-Smith norm? Can you show some light on that? I don't know what it is.
The Hilbert-Smith norm is the trace of the square.
Means only that.
Yeah, it's mainly that. For Hermitian matrices, it's that. And yeah, for example, for a pure state, it's the same, so it's just 1. If you have a mixed state, then this is smaller than 1, for example. And if you have other operators, you may have something that doesn't depend on the size of the system, or it may depend, because as it is a trace, you are adding all of the diagonal. So for example, for the identity, the square is the same, so you get the dimension of the system, right? Yes. For example, so if you want to estimate this observable with this method, it won't be efficient in the size of your system. Okay, and so here you have a more formal statement of the thing. Here there are like 3 parts, okay? This is the lemma 1, which is a result that they need for the proof. You don't have to understand everything, okay? Because some of you are with a face like... this is the statement of the theorem in a formal way, okay? So the previous one was the non-formal part, and this is the proof. So in lemma 1, what they prove basically is that the variance of an observable measured in this classical shadow only depends on the the set of unitaries. And it depends in this manner. And here we get this, our friend, the norm that depends on the shadow. And this shadow norm only depends on the ensemble of unitaries. So, for instance, this formula it's quite more simple for Pauli gates and for and for Clifford circuits. But basically, the idea of this result is that the variance doesn't depend on the state, but only depends on the ensemble that you are using to measure it. And using this and some performance guarantees for the median of means estimation, that's the algorithm that they use to estimate these values, it's quite straightforward to show that the variance of the result and the probability of success is bound as they state in the theorem. More or less, that's the idea. So it works mainly because the collection of that's the point. Okay, so examples. They give 3 examples and a counter example. So the first example is the fidelity estimation. In that case, your observables are of this kind. So their norm are bounded by a constant in the case of the Clifford measurements. So if you perform Clifford measurements, the number of copies that you need doesn't depend on the size of the system. And that's an interesting result. Whereas if you perform direct fidelity estimation, it can be even exponential in some cases, in some worst cases. By using this result, they are also able to show that entanglement verification via entanglement witnesses, so entanglement witnesses in the end are states that provide you with information about the degree of entanglement of the state, of the original state. So they show that entanglement verification with that approach can be mapped to fidelity estimation of many states. So in the end, it depends on the size of the set of witnesses that you are using. So using Clifford measurement, it's also quite efficient. It's polynomial in the number of witnesses that you are using. And for any local observable, Pauli measurements, their norm are quite well bounded, also by a constant. And so it's also dimension independent. So it's very interesting in those cases. However, if you have a global observable, then this method is not well suited for that because both Clifford measurements and Pauli measurements scale really bad because as it's global, the locality is all of the system and the Hilbert-Smith norm is not bounded. So yeah, in that case you have a problem. But for instance, this observable, the spin measurement, the spin of a system, the global spin of a system, it's quite easy to estimate with direct spin measurements, but it's not efficiently estimated with these classical shadow methods. And this is interesting because this observable is quite simple. If you want to estimate it and to measure it in a quantum state, it's easy to measure. But this method do not perform well in that case. And it's interesting. And I think that's more or less all I wanted to say. So regarding this thing that strangely that for such a simple observable, this method does not perform well, I think this is mainly related because the method is designed for arbitrary observables. So they focus on when you want to obtain classical representation of your system without knowing what you will be measuring later. So the results are mostly concerned on that, and they also use the norm of the operators and these kind of things, but they don't really focus on particular operators. So if you know, my intuition, I have not for that, but my intuition is that if you really know what you are going to measure, you can probably find better ways to represent your system. For instance, if you are only interested in the spin, measure the spin. Don't do this whole thing to obtain a quantum, a classical representation and that things. They also use single copy approach. Maybe this approach could be enhanced if you have many simultaneous copies of the system, maybe. And yeah, the main problem with this approach is that it cannot be used for global observables, but that's something that they also say. And they open like 3 main questions or outlook that future research could involve. For instance, can we use the classical representation of a system to analyze quantum evolutions of those systems? For example, if we evolve each of these classical images of the system in a separate manner, can you use those evolved states to estimate observables in the evolved real state, for example? Or can you use these classical shadows to represent a quantum channel instead of a quantum state? That would be another interesting question. Or the main also question, other sets of random unitaries could provide better results, or in particular better results for other sets of observables. For instance, maybe there are observables, sets of unitaries that are very good for global observables but very bad for local observables, maybe. So this is more or less what I wanted to share with you about this paper. I hope you enjoyed and learned something. And yeah, that's it. Thank you. This is the shadow norm for the one of the things and on the other one. Yes. So, is there any question or?
Do they perform any analysis on how much global the observable must be in order to be not useful for the like for example, if you want to measure some observable concerning 2 spins on 2 fields?
Yeah. Yes, they actually in the paper they also do some numerical analysis. And for instance, they use this to measure the correlation, the 2-point correlation, for example. And for 2-point correlation, it's quite efficient. What they find is that the efficiency in this case, it's not in the this is comparing against neural network tomography. And in this case, they don't find the advantage in the size of the number of measurements that the number of samples that they need also, but they find an advantage in the classical post-processing of the system, because this representation is much simpler than the other representation, for instance. But they don't go further into what are the limits of our own. No, they do this. They also use it to predict fidelities, and they compare 2 different methods for the GH state, and you can see that the cost in number of experiments of the classical shadow is almost constant, whereas this other method scales with the size of the system, for instance, and this. Yep.
But a global observable, you can transform it obviously using exponential number of gates. You can transform it into local one.
For any global observable, we transform it a local one. Of course, in general, it requires a lot of operations. So how? So here, I guess that you are assuming that you cannot perform, and so you are not increasing the depth of the algorithm. Imagine that you have a single power observable in one qubit.
Yeah.
If you perform 2 qubit gates, you start transform this observable into something that is more and more different. The opposite is also possible. So by unitaries, you can reduce and transform any global observable into a local.
Yes. Yeah, but I think they don't. They don't do these kind of things, because the observables only enter into play once you have the classical image of the system. So if you are willing to estimate global observables, then you should use a set of unitaries that gives you more information about global observables. So maybe this set of unitaries involves unitaries that are able to map global observables into local observables, maybe, I don't know.
Yeah.
But yes, but they don't change the, yeah.
So maybe you can transform, so everything that works, so if you know how to transform a global observable into a local one, so which is a unitary transform V one into the other, you can transform U.
Yeah, you can go transform U, and then, yeah. Yeah.
Okay.
Yeah, so once you transform U, you change the shadow norm and this stuff, and then the bound changes, and probably it will work better for what you have modeled. Yes. Yes, right. Okay, so if there are no more questions, you are welcome to share your papers in a sort of manner.